right, so welcome everyone to what I believe is the very last one of our 2023 to 2024 Maryland Robotics Center Seminar series for that particular school year. And so today we have Professor Christine Allen-Blanchette, who is an assistant professor in the Mechanical and Aerospace Engineering Department and the Center for Statistics and Machine Learning at Princeton University. And so today she's going to be talking about learning Hamilton dynamics from video. Let's give her a round of applause.
Yeah, thanks for the introduction. All right, so yeah, thank you also all for coming, and those of you who I don't know who or where you are, thank you for joining as well. So the methods that I'm going to talk to you about today, they focus on learning reduced representations from video. But while we typically focus on learning from video, or we're thinking about video for these particular methods, we do think of video as like a possible segue to other kinds of high-dimensional and entangled data like social networks, data, astronomical data, data from high-energy physics simulations, etc. And so the idea is that these data, similarly to video, can be very, very large, and they can also be produced at very high rates. So both the size of that data and its rate of acquisition are also projected to increase in the future. And so while this abundance of data can be like great, big data, we can learn more about the world with it. It also comes with like these huge challenges for data transmission, for data storage, and for our existing compute capabilities. So one way of addressing these challenges is with data reduction methods. So PCA or autoencoders, these are really popular tools for data reduction. And they're just, a couple of examples. But many of those examples can be sort of described as taking some input data X, compressing it with to a reduced representation with an autoencoder, F, and then using the approximate inverse of F, which is denoted G, to approximately reconstruct the input X as X hat. And this kind of approach can be useful in many settings, but a notable limitation or something that's missing here is that it's neglecting the dynamics of the underlying process, which can also be used to provide a reduction. Okay, so with a model of the reduced dynamics, we can estimate future reduced representations without requiring additional samples from the high-dimensional input space. Moreover, modeling the dynamics can encourage retention of pertinent high-level information in the reduced representation. So this is particularly important when we're thinking about using scientific data. So scientific data, we really need methods that can reduce the data dimension while retaining important high-level information. So we need this reduced representation to address challenges of streaming and storage, for example, and we need to retain high-level information for analysis, discovery of unknown quantities, and compute capability. And to achieve trustworthy analysis and compute, the reduced representation and our model of the dynamics should preserve physical invariants of the system, like the mass and the momentum. So this motivates the use of physics-guided deep learning methods for dynamical systems modeling, which can be classified into 4 types of methods. When the governing equations of the system are known, the solution can be approximated by a black box neural network whose prediction is encouraged to respect physical constraints using a loss function. When the governing equations are only partially known, so you have some white box information, we can use a black box to learn the residual. And these two categories, the neural network solution is guided by a loss function, which imposes a soft constraint. And in these latter two categories, the physics-guided architecture design and invariant and equivariant deep learning models, embedded knowledge of the system physics is incorporated into the neural network architecture itself, and so that's a hard constraint on the estimated solutions. Invariant and equivariant deep learning models can be viewed as a particular class of physics-guided architecture design where the network is designed to respect specific system symmetries. With this classification, you might suspect that, and then you'd be right that using soft constraints is sort of like maybe easier to design. And so it can be a lot easier to just pair a black box neural network with a physics-inspired loss than it is to design a neural network around prior knowledge of your system physics. But there's a trade-off between this ease of implementation and generalizability of your resulting solutions. So the methods that use hard constraints, while they're definitely more difficult to design, they generally produce much more interpretable solutions with greater generalizability than their black box counterparts. Okay, so then here's my shameless plug. Much of the work that we do in my group can be put into the categories of physics-guided architecture or invariant and equivariant deep learning models. So if you happen to be excited about these areas, we're definitely looking for a good postdoc. And the work that I'll talk about today, it mostly fits into this category of physics-guided architecture design, and it actually highlights some work done by Justice Mason. It's in my group. It's highlighted here. So approaches to learning Hamiltonian and Lagrangian dynamics from video, they fit into this larger landscape of works that can be organized by the dimension of the reduced representation they produce. So that's shown on the y-axis, and the dimension of the data that they consider. So this is shown on the x-axis. And the lower the representation dimension, so that's produced by the model, the more interpretable that representation is. And the higher the data dimension, we can maybe say that the model itself is offering greater utility, because understanding what's happening when the data is in high dimension presents a lot of challenges. So if we divide this space up into quadrants, the lower left-hand quadrant contains models that learn from state space measurements, usually. So this includes models like Hamiltonian neural networks and some other variants that incorporate constraints and control. This upper right-hand quadrant contains models that learn reduced representation from high-dimensional inputs where, although the representation learned is reduced in dimension, it's still much higher usually than the dimension of the underlying system. And so there are a couple really popular methods that do this. So Hamiltonian generative networks is one, variational integrator networks is another. And so these networks, they map images of 1- and 2-dimensional systems to latent representations whose dimensions are in the hundreds, for example. Okay, and so this lower right quadrant contains models that learn a low-dimensional and interpretable representation from high-dimensional inputs. And so this is where the work that I'll talk about today sits. So this talk, it'll cover three of our methods in this region of the space: RBNN, LogNet VIP, and HGAN. All these methods use Hamiltonian or Lagrangian formalisms to model the dynamics, but they have varying degrees of knowledge about the system that they're modeling. And these varying degrees of knowledge, we're sort of measuring them by these 3 questions. How do we select the latent dimension? How do we interpret that latent code? and also how do we model the transition dynamics. So in the first method, RBNN, which is a model that we use to learn the dynamics of a freely rotating 3D rigid body from video, we assume prior knowledge of the configuration space and structure. So and we use the Lee-Poisson equations to model the dynamics. In LogNet VIP, we assume knowledge of the configuration dimension, but not its structure. So that's something that we learn. And we use the Euler-Lagrange equations to model the dynamics. And in Hamiltonian GAN, we assume that we don't know anything about the configuration space, not its dimension or its structure. And we try to learn both of those things. And we model the dynamics with Hamilton's equations. Okay, so diving into RBNN, a neural network that learns the dynamics of a freely rotating 3D rigid body from video. If we think about like a standard autoencoder with an unstructured latent space and a black box latent dynamics, so this RNN module as kind of like a baseline, given a sequence of images of freely rotating rigid body, RBNN differs from that baseline model in two important ways. So first, that latent representation is structured. So we know the configuration space for this problem is the 3D rotation group, SO3. You see our freely rotating rigid body. And we incorporate this knowledge by structuring the latent space. So rather than mapping an input image to an arbitrary vector in Rn, like is done in a classical conventional autoencoder neural network, we map to two orthonormal vectors, v and u, which are on the sphere, S2. And we use those two vectors to construct a rotation matrix R, which represents the pose of the input image. So we have those two vectors on the sphere, and then we compute the cross product of those to get our rotation. So the second way that this network, RBNN, differs from a vanilla autoencoder is with the latent dynamics. So we know that the dynamics of a freely rotating rigid body, so we can use those to generate our latent sequences. So we take two consecutive frames of the video, map them to sequential rotations, which we can use to compute the angular velocity. With the angular velocity, we can use that together with a learned moment of inertia for this object to produce a representation of the angular momentum. And once we have that, we can use the Lee-Poisson equations, which I'm wrapping in this function RBNN, to compute future angular momenta. And with our learned moment of inertia again, we can use those to produce an estimate of the pose of future poses. Okay, so then the Hamiltonian formulation, it derives the equations of motion for a mechanical system using the symplectic form and a Hamiltonian. Hamiltonian is a map from our position and our momentum to the total energy of the system in this case. And for a freely rotating 3D rigid body, Hamilton's equations of motion evolve on a 6-dimensional space, which is a cotangent bundle of SO3. But then because we have this rotational symmetry for this system, we can write a reduced dynamics on a 3-dimensional space, which is the Lie coalgebra of SO3. And so this reduced Hamiltonian is given by this equation here, where J is a moment of inertia. And the corresponding reduced Hamiltonian formulation is shown here with an alternative symplectic form. And so all of that is incorporated into our RBNN, or this final equation is incorporated into our RBNN module. And we train this network end to end, and we simultaneously learn the encoding network F, the decoding network G, and also the moment of inertia tensor J without access to any ground truth phase-based measurements. So we train it with this combined loss function, which penalizes poor reconstruction in the autoencoder and also for the dynamics, and also penalizes latent dissimilarity between encoded and dynamics generated representations of the pose and also the angular momentum. So we compare this approach to two baselines, an LSTM baseline, which is like a RNN black box, which learns like next state prediction from the current state, and also a neural ODE baseline. So the neural ODE is also a black box, but it's a continuous model of dynamics. And we not only achieve a lower mean squared reconstruction error, but we do that with like many fewer parameters than the baseline models. And so in addition to these quantitative metrics, we also perform better in a qualitative sense. We can predict out to more than 50 frames with comparable qualitative performance as the baselines at around 10 frames. Okay, so yeah.
Where is the initial moment of inertia or moment coming from? The initial angular momentum.
So you mean like in the learning process, what is it initialized to, or what do you mean?
Yes.
Yeah, it's randomly initialized.
Okay. And then during inference, it's randomly initialized as well.
No. Oh, I see. Okay, so so we have something that's randomly initialized, and then in the training process, so as we are like seeing examples XT and we're minimizing this loss, it ends up converging to some representation. Right? And so then that's the representation that we use to do inference.
Sorry, yes, but there's an initial angular momentum that you have that you use to predict going forward in the dynamics.
Oh, I see. Here.
Right. So right here we have an initial angular momentum that has to come from somewhere. If it starts from 0, then we could hope it converges to the true thing as the sequence continues. Or
so this initial angular momentum that's computed with some initial moment of inertia tensor. Yeah. So our moment of inertia tensor. So we are training this model. In this case, this model is being trained for a single object. So the moment of inertia for that single object is.
Sorry, I mean omega t minus 1, where t minus 1
angular
is
velocity.
equal to -1. So where do you get the initial angular velocity?
I see. So our angular velocity, it's always computed for a pair of images.
I see. Got it.
Yeah. Okay.
Thank you.
Yeah, for sure. Yeah, I really like questions. It makes me feel a lot more comfortable to talk to people than at people. So if you guys like have them, please throw them out, you know.
I would like to look at your loss function for
Oh, it's this way.
minute, just
Yeah.
so I could take it all in. Yeah, so the understand the first term.
Yeah, this is like standard
I
autoencoder.
understand the last term. Okay, so then the second to last term is just making sure your rotation matrix is orthogonal.
Well, the rotation matrix, it's a rotation matrix by construction,
Okay.
but we have two mechanisms of generating poses. One is mapping from the image space to the latent space, which is through the encoder. But also, when we have these sequential pairs of rotations, then we can predict future rotations. And that's with the RBNN module. So we have we want it to be the case that rotations that we map to through the encoder for a given sequence match the ones that we generate with our RBNN module for that same sequence. And so we do that by penalizing when the rotation at time t generated by the encoder and the rotation at time t generated by the dynamics don't match. So that's this term.
And then the second term is the one that propagates forward in time.
Right, yeah.
And so to calculate this, you need 2 time steps of data.
That's correct, yeah.
But it's done like recursively rather than as a batch process where you take all your data initially.
Oh, I see. So actually, while we're training this, we have input trajectories that are length 10.
Okay.
And so this loss ends up just being over like 9, right? Is that helpful?
Yeah, I was just wondering if this training process is done, recursively, or if it's done like you just take all your data and you have one big batch process and you just crank it all in one step.
So for every individual trajectory, we compute the trajectory recursively using the dynamics, as you say. And for every pose that we produce with that dynamics module, we reconstruct. And so, yeah. So, I guess you're asking, is this just one step?
Yeah.
Yeah. No, it's all 10,
It's 10.
It's all 9, I guess.
I see. Okay, so it's from T0 to 9 or something like that.
And all of those are passed through the decoder module,
Yeah.
and we have a loss over all of them. Yeah.
So the estimation of J sort of comes out of that last term because it's built into the calculation of the momentum.
Yeah, I think that's right.
Cool, thanks.
Thank you. Cool. All right, so the next work that I wanted to talk about, so that one, in RB and N, we assumed quite a bit of structure, quite a bit of knowledge about the structure of the problem. We knew the configuration space dimension, and we also knew its structure, and we can embed like all that information into the latent space and make sure that everything, was as interpretable as we could. But I think, it's unusual to have all of this information at hand. So we have this desire to maybe move towards less structure. And so this work, Lagnet VIP, is sort of an intermediate, where we're learning Lagrangian neural network from video and incorporating less domain-specific knowledge in our architecture design, which allows us to model many different systems with minimal change to the architecture. Okay, so differently than a sort of the autoencoder baseline with the black box dynamics, Lagnet VIP uses Euler-Lagrange equations as a transition model, which imposes a velocity phase space interpretation on the latent code. So from Lagrangian dynamics, we have Hamilton's principle of least action, which says that motions of the mechanical system coincide with extremals of a functional S, which is the integral of this system Lagrangian, where the Lagrangian itself is given by the difference in kinetic and potential energy. So a corollary of this theorem is that the evolution of these generalized coordinates, which describe the configuration of the system, is subject to the Euler-Lagrange equations, which can be derived from the extremal of S. So when the system Lagrangian is given, we can compute the Euler-Lagrange equations we can compute the equations of motion by applying the Euler-Lagrange equations. So in our model, we design a Lagrangian neural network where the Lagrangian has kinetic energy with quadratic form. And this mass matrix and this potential energy function are parameterized by neural networks. So by using a Lagrangian neural network, we are in fact like imposing a velocity phase space interpretation of the latent code. And we use that to predict, and we use this interpretation together with the Euler-Lagrange equations to predict future latent states. So we train this network also end to end, and we simultaneously learn this encoding network F, the decoding network G, the mass function and a potential energy function, and train all of these components without access to ground truth velocity phase-based measurements. So we evaluate this model on synthetic videos, which were rendered in OpenAI Gym, so that's where these sequences come from. This is an example sequence of a pendulum, which is shown here, and here these individual images are the concatenation of 3 different frames, sequential frames, and then because it's a 3-channel image, we can view it as an RGB image. And so when this came out, so there have been a few works since this one, but when this came out, other Lagrangian neural networks that were used for video prediction, they either used latent spaces that had like much higher dimension than the number of degrees of freedom in the system, which means that they could be like really difficult to integrate into downstream processes, or they required explicit knowledge of the generalized coordinates. And so this model, I think, is something of a middle ground between those, where we use knowledge of the degrees of freedom, potentially provided by an expert, but allow for the possibility of integration to allow for the possibility of integration into downstream processes, but we don't require knowledge of the exact form of those generalized coordinates. All right, so then...
Can I ask you a question about
yeah.
the Lagrangian one?
Yeah.
So what does the expert provide?
So I guess an example, this is actually a good example with the pendulum, where an expert would tell us, like, okay, maybe you need, this system has 1 degree of freedom, but maybe we need 2 in order to represent it, but wouldn't, for example, tell us that, oh yeah, you can use the circle as the space for the generalized coordinates.
Okay, so it just provides the dimension of
What an appropriate dimension for modeling the system might be, yeah.
Gotcha. And then for that particular form of the Euler-Lagrange equation, I guess there's some assumptions about the types of constraints that are present in the original physical artifact.
Yeah, that's true. Yeah, so there are other methods where the Lagrangian isn't decomposed this way. I think that, yeah, that's certainly like an approach. I think here, knowing that the systems that we are modeling are these mechanical systems, and they have this structure, because we knew that and because we incorporated that, then we can pull out additional insights potentially by like plotting the mass matrix, for example, or the potential energy function, that result.
Well, like for example, do you have to assume there's holonomic constraints, or can you accommodate non-holonomic constraints or time-varying constraints?
So with this model, we don't have a way to incorporate constraints, but there are. I mean, there are other models, not ours, that incorporate constraints really easily. Yeah, that's a good point.
Can I ask a question?
Yeah,
Just out of curiosity, and maybe this is what you're going to address next. What if your expert is not that good, and so they need 3 to model the pendulum?
Yeah, like you just want to throw away your expert. Yeah, that is what I'm going to talk about next. All right, let's get to it. HGAN, so this is a Hamiltonian neural network embedded in a GAN framework, which is a generative adversarial neural network framework. And here we assume that, well, I mean, I guess it's not exactly like throwing away not exactly if your expert fails you, but it's sort of more like throwing away an expert altogether, where we assume that we don't have any knowledge at all about the configuration space dimension. We assign it arbitrarily, and this framework allows us to attempt to discover that structure using this configuration space map that we introduce and our cyclic coordinate loss function that we also introduce. All right. So just like a primer on GANs, a standard generative adversarial network. So the GANs are popular tools for learning to generate images. So here's a cartoon of a GAN where examples X from the data set, where we have examples X from the data set, and we also had synthetic samples X hat that are produced by a generator which acts on a random sample Z. And these samples, the true samples and the fake samples, are passed to a discriminator, which is tasked with predicting whether or not they came from the data set or whether they were synthetically generated. And both these networks, the generator G and the discriminator D, they're trained together in an alternating minimization, maximization, optimization. So GANs for video generation have this additional component, many of them, where now they're taking a sample from some noise distribution, usually a Gaussian, and they're mapping it to a sequence of samples, which are all individually decoded by the generator to image samples. And all of those images together are understood as a video. So then we have two discriminator networks in this case, one that checks to see if images look real or fake, and one that checks to see if our videos look real or fake. This structure, if we're hoping to learn interpretable representations, doesn't quite meet our needs. So there are three reasons for this. One, that recurrent neural network is a discrete black box transition model. So we'd like to use instead a Hamiltonian or Lagrangian neural network for interpretability. Also, if we try to do a visualization of these latent states, there isn't really a clear way to extract any information about the structure. So looking at these samples here that are projected to 2D using t-SNE, it pretty much just looks like noise, pretty much the same noise that went in. And also three, when we look at this structure, when we use this structure for our specific learning problem, we find that these generated sequences don't actually mirror the training data at all. So this top row is a synthetic, of course it's synthetic, but it's supposed to show the motion of a pendulum where the mass itself is rendered as a Gaussian blob. So this is an example from our data set. And this trajectory on the bottom is an example of the videos that are produced in this architecture. So the sequence generated by this RNN-based GAN, it shows that the model has captured the fact that there is color variation in these sequences and also size variation in these sequences. But it's showing that variation across, within a sequence rather than across sequences, and it doesn't have any of the sort of temporal structure that we'd expect. So as a first kind of way of trying to get the structure that we want, we can embed a Hamiltonian neural network here in the place of our recurrent neural network. And then we can learn to generate image sequences that look like the sequences that were in our data set. So here's an example of a pendulum sequence that was generated by this network. But when we visualize the latent space, it actually turns out that we haven't learned any discernible structure. It looks like noise, exactly how it did when we used the RNN. So we remedy this by incorporating an additional network F, which we call our configuration space map. And so this map is transforming the space PZ to an intermediate space that can offer some insights about the structure of the configuration space. We also incorporate a novel cyclic coordinate loss function that penalizes non-zero values for the change in momentum. And this loss function encourages the configuration space to be minimal. And then with these interventions, when we go ahead and look at the structure of the configuration space, we can see that we have structure and we haven't sacrificed qualitative performance. Our resulting videos look quite similar to the ones for the HNN cell. Okay, so this is, in summary, while our approaches to learning dynamics from video, they exist on a spectrum of explicit constraints, each of them maintains the interpretability, which is important when we think about incorporating learned solutions into downstream tasks. RBNN requires knowledge of the degrees of freedom and the structure of the configuration space at design time. LogNet VIP, it only requires knowledge of the degrees of freedom, and HGAN attempts to discover structure and degrees of freedom from the configuration space during training. So thanks again thanks for your attention and your questions. If there are further questions, I'm happy to receive them. Thank you. Oh, yeah.
So in the examples you showed today, the objects were almost at a fixed distance from the camera, which means that the scale ambiguity of vision didn't come into play. Have you considered how scale ambiguity may affect your representations?
Yeah, thanks for asking that. So, I mean, yeah, for the most part, that's true. I think there's like that small, the RBNN example, there's like rotation into, toward the camera. So there's a little bit of depth that we have to infer there. So I guess, so we have a couple of thoughts about when there's a scale ambiguity. So like if we're observing multiple systems and there's some kind of like rotating towards the camera or something like that, then we would consider that there. I think that we aren't super concerned about, I expect that our method generalizes to those situations, just because of what we've seen with the RBNN, with the camera rotating into the with the object itself having changes in depth. Yeah, thanks.
Thank you.
Can you go back to the HGAN sort of final slide? So I want to make sure I understand. So you feed in Z1, and from that you predict your synthetic data x2 hat through xn hat, which you compare to the real data.
Oh, yeah, there's no real data in this. Oh, wait, this, which I compared to the real data. Yeah.
But where does where does Z1 come from? That's what I'm confused about.
For sure. In this like sort of generative pipeline, we're taking a sample from a noise distribution, like it can be any one that's easy to sample from. Usually it's a Gaussian. And that's where Z1 comes from. It's just noise.
Okay. And it's just a single sample?
And it's a single sample, yeah.
And then you propagate that along your estimated dynamics.
Yeah, so first it's being passed through this F that we call a configuration space map. So the idea is that we're like taking data that is from a Gaussian and sort of mushing that Gaussian potentially into the shape of the configuration space for the system that we're modeling. Okay. And then once we're on that shape, then we're using a Hamiltonian neural network to create future samples.
And some of these blocks are learned by the degree to which x hat matches x?
Yeah, right. Yeah, all of them. So the ones that are darker are black boxy. They're pretty much straight up neural networks. And then this gray one, has the Hamiltonian structure, but it still is a Hamiltonian that's parameterized by a neural network. So, yeah.
Right. And so the blue dots are meant to show the evolution of that initial sample in the configuration space?
Yeah, okay, so that's a little bit misleading. So thanks for pointing that out. In this case, this visualization comes from taking a bunch of samples here at the start and passing all of them through F to get a sense of what the new, like what the learned configuration space structure looks like. Gotcha. And so the idea here, although it's not plotted, is that a trajectory Z2 through Zn would be something that's traveling through this space.
Yep. And so when all is said and done, what you achieve is HNN. Right? You achieve a mechanism to propagate the dynamics.
Yeah,
That's
well,
what
I guess
you're trying to achieve.
so. There are two. I think there are two things that result here. One is that like this is for the pendulum example, and it's also true of other. So like yeah, we can also do this. Like there's a two-body system, toy two-body system also in this data set, where we are learning that the configuration space is like effectively one-dimensional. And so this isn't something that the other methods in the landscape of methods or that I presented in this presentation have shown that they're able to do is discover like the structure and dimension of the configuration space. So that's pretty exciting, I think. The other thing is that we're able to generate synthetic sequences. So, I mean, it's a generative model that's not unique to us, but we can generate what I would say are physically plausible sequences using this machinery. Yeah.
So like this architecture served during the training phase, but during the testing phase, would you no longer have the D?
Yeah, you'd cut this whole thing off.
Yeah.
Yeah.
Got it.
Yeah.
Have
Thank
you,
you.
So this seems to fall into sort of like the general category of neural networks that learn dynamics, right? That learn times and predict time series, right? Because most neural networks are used for like classification and other tasks, but this is sort of in the realm of being able to, like I said, in the testing phase, you're basically just propagating forward from an initial sample. And so another type of neural network in that same like realm, I think, is like a reservoir computer, like a non-recurrent neural network, whereby you can train it on time series data, and then in the testing phase, it can predict the time series data, and that uses like it doesn't actually invoke like the physics, right? You've got like the Hamiltonian dynamics kind of like embedded in your neural network in your loss function, and so I'm curious if you've like thought of like how does this fit into that other body of work?
I don't know what a reservoir computer is.
Okay, yeah,
I just wrote it down.
Here.
Yeah.
I think like University of Maryland folks use it a lot.
Nice.
It's a non-recurrent neural network. And
so what does that mean, that you predict all of the entire sequence at once? Or
no, it's like so if you have time series data, you can train the input output weights of basically like a sparse graph neural network, and such that in the testing phase, it can propagate the time series forward in time, and it does a pretty good job for a certain amount of time before it starts to deviate from the ground truth.
Okay.
So you train the network to learn the dynamics when you don't have like a first principle model. You don't have a state space representation of the dynamics. You just have data.
Mm-hmm.
So that's why I say it's like kind of in the same realm.
Yeah.
As what you're doing, but
yeah.
One main difference is it doesn't, as far as I know, have any like of the intrinsic physics in it.
I see. But I imagine, so yeah, I don't know, so you'll guide my commentary if I just go off the rails, but it's like from what you've described, I'm not sure I see why you wouldn't be able to embed the physics. Is that?
Maybe. Yeah, I don't.
Like, I mean, so what I'm imagining actually is that you have some input sequence of some length, and then there's like a mapping that's produced from that. Like instead of mapping to a scalar or something or a vector, you're actually mapping to a function. Is that right?
Basically, in the training phase, you train the output weights of the neural network.
The output weights of the network. Yeah, so you're like learning a network from
The network is usually kind of just a big sparse graph,
Yeah.
and then what you're training is the output weights of that network.
Okay.
So yeah, there may be a way to take the methodology and like the philosophy that you have and apply it. I'm not aware of,
Yeah.
of that.
I don't know, like maybe that graph, oh, you have some output weights, but I don't know what you mean. What are output weights? What are output weights used for?
I think, again, I'm not too familiar with some of the terminology used, but I think it would be like your decoder.
Oh, I see. Yeah, so does it seem plausible that you'd be able to arrange these weights in the decoder so that they correspond to physical quantities that you're interested in?
It's possible. I don't think that's normally done. I think it's normally kind of just you get what you get. But yeah, anyway, might be something to look at because at the end of the day, both the methods that you presented and this other body of work, they're predicting time series without having models, of the system, just the data.
Mm-hmm. Yeah, no, that's, thanks for putting me onto literature. Connecting me with that body of work.
Yeah, and some of the chief proponents of it are here in Maryland, so I can put you in touch with them if you're interested.
Yeah, that would be cool.
Take a look at it and see if it is at all similar to the kinds of things you're working on.
Yeah, thank you. Yeah.
Maybe just for some of the undergrads, like in the room and watching online, anything in particular that you're very excited about, like particular applications to which you would be applying this to that you're excited about in the future? It could be near future or like long-term future, something that this particular pathway would enable.
Yeah. Okay, so I think like my favorite extension is one that we think about with the rigid body neural network thing. And I think my favorite, I guess there are like a few. There are a few. So here, one thing that that is like a limitation, I would say, of this approach. And I think, for the most part, all the approaches in this class is that you have to model one system at a time, or that it's like the machinery is designed to model one system at a time. Because you're learning this moment of inertia, which is like fixed, right? So we are kind of fiddling with the idea of like how could we make this so that we can learn multiple systems with one architecture. I think that would be like a useful thing to do and an exciting thing to do. Another direction that I think is super exciting is the idea of like, how can you know when a trajectory that you observe is not consistent with the physics that you've modeled? So if you detect an anomaly. So if we're thinking about this freely rotating 3D rigid body, if we're thinking that maybe it's a spacecraft or something like that, and it's like moving in space, it has some dynamics, we've modeled it. We have this moment of inertia tensor. Okay, cool, we're doing a great job of predicting the future. And then all of a sudden we're getting like, measurements from the system that are inconsistent with the dynamics that we've learned. It's always going to be a little bit inconsistent, right? Because there's noise. And so at what point do we know that something like happened to our satellite or whatever that we're observing? When do we know that something must have happened, like maybe a piece fell off or something like that? And so being able to like have a representation of the uncertainty in our measurement, so that we can have some way of saying when something has gone wrong. I think that's also like kind of an interesting way to go. Thanks.
Great. Any other questions? Yeah.
Yeah, great talk. Two quick questions. One, I was thinking, about the Lagrangian model, right? So what happens, for instance, if in your system your dynamical system, actual system, there is going to be a large reconfiguration. Let's say it's going to encounter, I don't know, mechanical instabilities or an event, that, I don't know, buckling or a snapping or something that, you know, is a very sharp.
Oh, the Lagrangian network. Yeah.
Yeah, because we can model that, right, with our equations. Will this algorithm be able to follow up with that, to predict that, the type of instabilities? And then, okay, I have a second question, but you know, maybe.
Oh, can I recover instability?
Yeah, can you recover any sort of instability,
I-
large, you know, sudden reconfiguration of the system?
Yeah, I really like that question. I don't know how we would do that. I think maybe if this is observed in training, then maybe there's like it would be able to model it, but certainly not naively. I don't think that it would be able to. You'd certainly have to see it in training, and then beyond that, I'm not quite sure. So I don't actually know much about modeling instabilities like the ones anyway that you and I have been talking about. But yeah, I'm not exactly sure what you would want to change here, or if you would need to change something here beyond having examples of this change in the training set to be able to model those. But yeah, I think that sounds super exciting for sure.
Yeah, because for instance, you know, buckling is a form of, you know, pitchfork bifurcation. Right?
Oh yeah.
This is just, I don't know if you go along that route with the Hamiltonian.
Yeah. So with this, yeah. So thanks. Yeah, thanks for asking. So we have another line of work where we like explicitly try to deal with systems that have bifurcations, but not here actually.
Okay, second question then.
Yeah.
So all this applies to rigid body dynamics.
Yeah.
Right? What if there is a soft body forming, right? For instance, you show the imaging of a CT scan, right? Those are soft tissue that expand and contract, or you know, you can still write equations of motions for those, right? There are certain terms of nonlinearity. This comes from the elasticity, viscoelasticity of the material, you know, quasi-linear viscosity. So
yeah,
so that maybe applied to that case, and what would be the best approach in your opinion to go along that route?
Yeah, I definitely don't know the answer to that, but I have thought a little bit about it, and what I think would be a useful approach to doing that is if you like pretend that this soft body so like that it's like a rigid body but a bunch of connected rigid bodies, and in that way just like have this latent space. So I made this argument that you don't want a latent space that's like super high dimensional for a system that is low dimensional, but maybe if you have this latent space that's super high dimensional for something like a soft body, then maybe you are able to use this kind of structure in order to be able to model those systems. That's the extent that I've thought about it. But yeah, I think that's cool.
Thank you.
Thank you.
Any last questions? All right, let's thank our speaker.
Thank you.
So we'll have a little bit of time just afterwards. So for those who want to stay, you can ask them questions. Otherwise, that's it for the semester. That's for our MRC Symposium series. So have a fantastic summer, especially for those online. And we'll see you all when we get back in the fall for what is to be an exciting lineup as well. Bye, everyone.
Bye, everyone.